let's work through this arc length handout. So as usual with these handouts, you should download a copy for yourself and work through as much as you can before you watch this video, and then watch just enough of this video to get yourself unstuck from wherever you got stuck, and then continue on your own. Once you've worked through the whole thing, if you'd like to watch this video to sort of see how I work through these ideas, then that's fine. But you will get a lot more out of this if you work on it on your own for yourself, but rather than just watching me work through it. So with that said, the setup here is that we have some graph of a function. There's this little bit of arc length along the function, and the idea is we're zooming in so close to the graph of a function that this bit of arc length is practically a straight line, even though the graph itself, on a large scale, it curves. On a small scale, since we're zoomed in so far, it's essentially straight. dx is an infinitely small step in the vertical direction, and dy is the corresponding vertical small step in the vertical direction. dy and dx have to be in a certain ratio so that this chunk of arc length actually points in the direction of the curve, right? And that direction, the ratio between dy and dx is dy dx, which is the derivative. That's why dy dx is used for the notation of the derivative. So at this point, go ahead and pause this video and see if you can use this diagram to come up with some way of writing ds in terms of dx and dy. Okay, so I hope it occurred to you that this looks like a right triangle here. In fact, it has to be a right triangle because dx is in the x direction, dy is in the y direction, and those directions are perpendicular. So we do have a right triangle here. And since it's a right triangle, we can use the Pythagorean theorem. The Pythagorean theorem says the square of the hypotenuse, which is ds squared, has to be equal to the sum of squares of the other sides. So that's dx squared plus dy squared. All right, so we've expressed ds somehow in terms of dx and dy. So go ahead and pause the video and have a look at the next part. Okay, let's look at part B. So rewrite dy in our expression in terms of dx. So if you look at this expression, right, if we want to, we could take a square root on both sides. So ds is the square root of dx squared plus dy squared. Normally, we would need a plus or a minus when we take square roots on both sides of an equation, but arc length has to be positive. It doesn't make sense to have negative arc length, so we're choosing the positive square root here. So for part B, it said that we should rewrite dy in terms of dx. So, right, we're starting out with ds equals the square root of dx squared plus dy squared. And dy is dy dx times dx. That's it. It looks obvious because it looks like, hey, you can just cancel these dx's like this. But remember that this is more or less a definition of what dy means, because dy dx isn't actually a ratio of numbers, it's a derivative. We write it as if it's a ratio of numbers, even though it isn't really, technically speaking. So, but the notation makes this look obvious, so that's an indication that the notation is good notation, right? Good notation should make things that look obvious actually be true, even if they aren't obvious. So we can put this expression in here for dy. That gives us, right, dy dx times dx. Okay. And then if we want to, right, we could simplify this. So it looks like this is square root of dx squared plus, so multiplying out this squaring, we get dy dx squared times dx squared. Now both terms inside here have a dx squared, so we can factor that out. So ds is the square root of 1 plus dy dx squared times the square root of dx squared, but that's dx. Okay, so here we've written ds in terms of dx. So go ahead and pause the video and have a look at part C. Okay, so part C, we're going to rewrite the dx up in our original expression for ds, which, remember, the very first expression we got for ds was the square root of dx squared plus dy squared. So in part B, we rewrote dy in terms of dx, but here for part C, we can write dx in terms of dy. So dx is dx dy times dy, right? So here we're sort of treating y like the independent variable instead of x. And if we put this in, we get ds is the square root of dx dy times dy all squared plus dy squared. This looks very similar to what we got up in part B, so we can do the same sort of simplifying, right? This is the square root of dx dy, sorry, that should be a y right here, squared times dy squared plus dy squared, square root of that whole mess. So now we can pull that dy outside of the square root, and we get the square root of dx dy squared plus 1 all times dy. So there's this nice symmetry, right? So this is ds again. There's this nice symmetry between how we express ds in terms of x and in terms of y. Right? These basically look the same, it's just the roles of x and y have interchanged, which makes sense because, right, arclength doesn't really care which variable is the independent variable. Right? Arclength is measured the same either way, so it makes sense that the expressions for ds have this symmetry. All right, go ahead and pause this video and look at number D. Number D. How about letter D? Okay. So ds is the length of that little piece of a graph. So what does this integral calculate? Well, remember, a definite integral, right, if we have some function, y is a function of x here, and we're going from an x value called a up to an x value called b, ds is a little bit of arc length. So at every point along here, we have a little bit of arc length called ds. And how long this little bit of arc length is really depends on where you're at along the graph. So all of these are called ds. And an integral adds things up. So this integral is going to add together all of these little bits of arc length, starting at x equals a and going to x equals b. So what's that going to give us? Well, if you add up all of the little bits of arc length from a to b, then what you get is the total arc length. From along the graph from x equals a to x equals b. All right, so this integral is what we'll want to evaluate if we ever want to find an arc length. Of course, to actually evaluate this integral, we'll have to use one of these two expressions from the previous two parts, either express ds in terms of x to make this an x integral, or express ds in terms of dy and make this a y integral. And in principle, you can do either one, but of course, in practice, usually one or the other is going to be easier. And so in practice, you choose whichever one's going to be easier. So pause the video and have a look at part E. I guess it's number 2 instead of part E. So let's find the length of this graph from x equals 0 to x equals 2. So just this first portion of the graph. Right? And we know how to calculate an arc length. You just integrate ds. Now we're going to have to decide which is the variable that we want to make the independent variable. The way this is currently expressed, it looks like x is going to be the independent variable. In principle, we could solve this equation here for x, and then we'd have y as the independent variable, but it doesn't seem like that would really get us anything. Probably it looks like it would be about equally difficult either way, so there's no reason to switch to making y the independent variable. So if we're going to use x for our independent variable, then we have to use x bounds, so x equals 0 to x equals 2. Also, we need to write ds in terms of dx, if we're going to use x for our independent variable. Fortunately, we did that in earlier parts. So this ds in terms of dx is the square root of 1 plus dy dx squared all times dx. Okay, and now this is something we can actually hope to evaluate. So dy dx, right? Remember, y is right here, so we can calculate dy dx. Dy dx, that's just calculating a derivative. So do the power rule. We're going to get 3 over 4 times x to the 1/2, it looks like. Okay, and now we can take this and put it into our formula over there. We get, let me put it over here, just in case I need to use this space over there to calculate. So we get the integral from 0 to 2 of the square root of 1 plus dy dx squared, so that's 3 over 4 x to the 1/2 squared dx. Okay, let's simplify that integrand. So this is the integral from 0 to 2 of the square root of 1 plus, looks like 9/16 times x. Right, the square root and the square undo each other, so that's nice, dx. And now we need to evaluate this integral. Right? As usual, once you have written down the integral that you want, you can temporarily forget where it came from and just think about what tool in our integration toolbox do we have that might handle this situation. And I think a u substitution would be a good idea. So if we do a u substitution with u equal to 1 plus 9 over 16 x, then du is going to be 9 over 16 dx. And so 16 over 9 du will be equal to dx. So now we can rewrite our integral in terms of u's. While we're at it, let's switch the bounds. So when x is 0, u is 1. And when x is 2, u is 1 plus 18/16, I guess. So that's going to be 1 plus 9/8, so that's going to be 17/8. Okay, and the integrand now is just the square root of u, and dx turns into 16 over 9 du. Okay, so let's pull that 16 over 9 outside. Integral of the square root of u is 2/3 times u to the 3/2. And we need to go from 1 to 17/8. Okay, so 16 times 2 is 32 over 27 times 17 over 8 to the 3/2 minus 1 to the 3 halves, so minus 1. Okay, it's possible we could simplify this a little bit more, but I'll leave it like this. If you really want to know what this is, you could do some algebra to simplify this, or dump it into a calculator if you want a decimal approximation. All right, so sort of the big picture here is if you want an arc length, you're going to integrate ds. You have to choose which independent variable you're going to use, express ds in terms of that variable. Once you have that, so you need to evaluate one derivative here, right? That comes from whatever curve you're trying to find the arc length of. And once you have that derivative, put it in, and you have some integral to calculate, and then just work out that integral. All right, let's look at another example in number 3. Try to work it out for yourself before watching me do it. Okay, so let's try number 3. Let's find the arc length of this curve. It's x equals 1 over 6y cubed plus 1 over 2y. And we're going to go from y equals a half, which is right here, to y equals 2. So that's going to be this part of the curve. It looks like from here to about there. Okay. We have to decide, right, we know we're going to integrate ds, but we have to decide, are we going to use x as our independent variable or y as our independent variable? Well, this equation is already set up to use y as the independent variable, and in fact our bounds are given in terms of y, so why don't we use y for the independent variable? So this is going to be the integral from y equals a half to y equals 2. And we're going to integrate the square root of 1 plus derivative of x with respect to y squared dy. Okay, now we need to evaluate this integral. We need to figure out what is the derivative of x with respect to y. So we can calculate that down here. Remember, this 1 over 2y, this is really 1/2 times y to the minus first power. Writing it this way is going to make it a little easier to differentiate. So dx dy is, using the power rule, it's 1/2 y squared plus, minus 1/2 y to the minus second. Okay, so now we can take that and put it into our arc length integral here. So integral from 1/2 to 2 of the square root of 1 plus, and then we put dy dx in here, so 1/2 y squared minus 1/2 y to the minus second squared dy. And I'll tell you right now that arc length integrals are often a mess because they always have this square root in them. So often arc length integrals will involve a bunch of messy algebra, and you have to be extremely careful to get all of that algebra exactly right. Because if you slip up a little bit, right, usually what happens is we need to do some algebra to make this square root simplify away, is often how it works. Not always, but often. And if you make an algebra mistake, you won't be able to simplify away this square root, and then you might be stuck. So be really careful about your algebra when you're working with arc lengths. Okay, so that said, I guess what we're going to have to do is multiply out everything inside of these parentheses here. So let me do this down here. So integral from 1/2 to 2 of the square root of 1 plus 1/2 y squared times itself is going to be 1 over 4y to the 4th. Okay, now we do twice the product of these two, so that's going to be minus 1/2 y squared. No, I'm sorry, minus 1/2, right? Because the cross terms, when you're squaring something, the cross terms are twice the product. So twice 1/2 y squared times minus 1/2 y to the minus second. So we get 2 times a half is a half. There's only one negative, so we get a minus sign in the middle here. And y squared times y to the minus second is 1. So there aren't any y's in this cross term. Okay, and then the second piece gets squared, so plus 1 over 4 y to the negative fourth. Okay, this is all dy. All right, I guess continuing to simplify everything inside of the square root, we get integral from 1/2 to 2 of the square root of. The only thing that simplifies is there's a constant term in front, 1, and there's a constant term in the middle here, minus 1/2. So that those add up to give us 1/2. So this simplifies to 1 over 4 y to the fourth plus 1/2 plus 1 over 4 y to the minus fourth, all times dy. Now, if we're hoping to somehow simplify this so that the square root goes away, then hopefully the stuff inside the square root is a perfect square, because then the perfect square and the square root will undo each other. So we should think about factoring the stuff inside of the square root. But if you think about factoring it, look, it looks exactly like what we got when we multiplied out the squaring to begin with, except instead of a minus in the middle, it's a plus. So that means when we factor this, it's going to be this same perfect square, except instead of a minus right there, it's going to be a plus. So when we factor this, we get integral from 1/2 to 2, the square root of, so this factors as 1/2 y squared plus 1/2 y to the minus second, all squared. Okay, dy. So if you're not quite sure about that, you can multiply this squaring back out and just check that you do get the same thing as the line before. Okay, so now we have a square inside of a square root, so those undo each other. We get the integral from 1/2 to 2 of 1/2 y squared plus 1/2 y to the minus second. And now everything is just a sum of powers of y, so now we can integrate using the power rule. So we're going to get, let's see, 1 over 6 y cubed minus 1/2 y, minus 1/2 y to the minus first. And this is from 1/2 to 2. As usual, just really quick, check that this is a correct antiderivative by taking its derivative and seeing if you get back to your integrand up here. So power rule on this first term gives us 1/2 y squared, right? And then power rule on the second term cancels that minus sign. We get 1/2 y to the minus second. Yeah, okay, that's correct. So now we can do all the arithmetic of evaluating our bounds here. So 1 over 6, 2 cubed is 8, minus 1/2 times 2 to the minus first is 1/2, minus, and then plug in 1/2. So 1 over 6 times 1/2 cubed is 1 over 8. Yeah, yes, minus 1/2 times 1/2 to the minus 1 is 2. Okay, and now we have a bunch of arithmetic to do. So this is going to be 4 over 3, so 4/3, minus 1/4, minus, and then in here we get 1 over 48 minus 1. And this is a bunch of fraction arithmetic, so I'll let you work that out. One thing to keep in mind is that this arc length integral should give us something positive, because arc lengths are always positive. You can't have a negative arc length. So whatever this comes out to be, if you get a negative for your arc length, you made a mistake somewhere, so you should definitely go look for a mistake. Second point is, if you have a graph of the arc that you are finding the arc length of, you should be able to just approximate the arc length just based on the graph. And that will give you some rough idea of what your answer should be. So, if you imagine pulling this red line segment perfectly straight, it looks like it would maybe be about this long. So whatever arc length we get when we evaluate all that fraction arithmetic down below, it seems like we ought to get something in the neighborhood of 2. It's actually a little bit tricky to see if it's going to be a bit smaller than 2 or a bit larger than 2, but somewhere in the neighborhood of 2. should be our final result. Right? And if we evaluate some of this, so 4/3, this -1 here is actually plus because of the minus sign in the middle here. So we're going to have a +1 minus 1/4 minus 1/48. So 4/3 plus 1 is 7/3 minus 1/4 minus 1/48. Right? 7/3 is 2 1/3, and we're subtracting 1/4. So this is just a little bit bigger than 2. So it looks like we are going to get something in the neighborhood of 2. So, that convinces me that we didn't make any sort of gross algebra errors as we did this calculation. So with calculating arc lengths, since it's so easy to make an algebra mistake along the way, and also it's easy to just make an arithmetic mistake when you're evaluating with your bounds, when you're done, take a second to think about the value that you got for your arc length, and just try to get some rough idea of if it's plausible or not. If you make some gross mistake, you might get an arc length that is obviously way too big, or obviously way too small, or even negative, in which case you definitely made a mistake.